The other kind of calorimetry problem that you will encounter is what we do with a bomb calorimeter. So typically the words in the problem will say bomb calorimeter in it. So just remember it's that sealed vessel that has all the other materials in there. And the big thing in there with a bomb calorimeter, you should have a capital C, which is the heat capacity of the bomb calorimeter. So that should be somewhere in the problem on here. So what we're doing in here is we are taking this mass of glucose and we're burning it inside of a bomb calorimeter. So we are performing a combustion reaction. So in a combustion reaction, it should be exothermic, so we should be releasing heat. The temperature of the calorimeter increased from 23.8 degrees Celsius to 35.6 degrees Celsius. And then the calorimeter contains 775 grams of water, and the bomb itself, so here's the key, it has a heat capacity, and look at the units there, 893 joules per degree Celsius. So we know we have a capital C on here. And now the question is how much heat was produced by the combustion of the glucose sample. So we need to go ahead and remember the sum of all the Q's are going to equal 0. So then we have to ask ourselves, what are the Q's that are in the problem? So the Q in there, we have our Q of the reaction, and that's the combustion of the glucose. So there's a combustion that's happening there. Plus, we know that we have water in the calorimeter. Plus, there's going to be a Q of the water because there's going to be some heat transfer of the water itself. And then it tells us the bomb has some sort of heat capacity. So then there's a Q of the calorimeter. We're going to add all those up to be 0. So if we go back to what is the system and what are the surroundings, this Q of the reaction is what we're interested. So that's our system. Everything else is our surroundings. But I like to break it up into the separate Q's. So we don't know what our Q of the reaction is. We can calculate the Q of our water as the m lowercase c delta T. So that's our mass, specific heat capacity, and our change in temperature. And then we are also told what the heat capacity of our calorimeter is times delta T. So our change in temperature and how that will all equal 0. So this is what we want to calculate. We know that we have our mass of our water is 775 grams. Our C is 4.184 joules per degrees Celsius grams, or you'll see grams per degree Celsius. And our change in temperature is going to be 35.6 minus 23.8 degrees Celsius. Our capital C on here is given to us as 893 joules per degree Celsius. And then we're going to multiply that by our same temperature final initial. So our delta T is 35.6 minus 23.8 degrees Celsius on here. So we can go ahead and calculate this out. Our Q, the reaction, if we end up calculating all of this out, we should get a value of 38,300 joules. We calculate this out over here, and we should have 10,500 joules. We set that equal to 0. So we go ahead and add this up, our Q of the reaction plus 48,800 joules equals 0. And then our Q of the reaction should equal negative 48,800 joules. And that should make sense to us. Because we have a negative number, we should have some sort of exothermic reaction. So we have a negative value. It makes sense in terms of the combustion of our glucose. And a lot of times what we will do is we will actually report these values in kilojoules. So make sure you look at your answer to see what units you're going to use, because you may have to convert this as minus 48,800 joules You might have to convert in kilojoules. There's 1 kilojoule for every 1,000 joules. I never skip writing these dimensional analyses. So you will get a final number of minus 48.8 kilojoules. So you'll have to look at your problem to see which value you might be calculating, whether it is kilojoules or joules.